Hi, welcome to Optimizing Your App Engine app. I'm Marzia Niccolai.
I'm Greg Darke.
And I'm Troy Trimble.
And we're going to be talking to you today. Here's a little overview of the agenda that we'll be covering. First, we're going to go into some coding tips on how to write your App Engine app more efficiently. Then we're going to cover some performance settings. And then we're also going to talk a little bit about what we're planning in the future and how this will impact the way you scale and write your app. First, just want to talk a little bit about latency versus cost, which is really what we're trying to cover here when we mean optimizing. Now, these aren't always conflicting goals. Sometimes these things are conflicting, and sometimes when you optimize for one, you optimize for the other. My general rule of thumb when I think about these things are, if I make something more efficient, that's generally also going to lower its cost. If I'm using more resources to accomplish lower latency, that's usually going to be higher costs for me. And sometimes, with App Engine and the way we have our performance settings available, you can choose to lower the amount of resources you're using, and it's going to be less cost, but it's also going to be slightly slower latency. Now, the other question is, what do we mean by good latency? So I've put up a slide here from an admin console graph on an application that I work on, and I've highlighted your lowest latency handler and our highest latency handler. Now, for the base handler, 46 milliseconds, I'm just going to say I think that's pretty good. It's what your user's going to hit the first time they come to your app. 46 milliseconds, they get something served to them. Now, the highest latency handler, you're going to ask, 942 milliseconds, basically 1 second. Is that good or that bad? Well, I mean, a lot of that depends, and a lot of that really covers like the heart of what we're talking about today, which is, well, who's seeing that request? If your user seeing that request, is a second good? But if it's just some request running in the back end, maybe I don't care if it's 942 milliseconds. Of course, in this case, it's something that's asynchronously requested but served to my user. So I see that 942 milliseconds. I'm saying, well, it's not bad, but could I be doing something better? I probably could. Apparently, I have to be standing here to get the thing to work. OK, so I just want to say that we're using Python here for our code examples, but really, a lot of these things are not language agnostic. When we do say something that's language specific, we'll call it out. And even the Python, please don't copy and paste this Python in your app, because it's more as an example of good and bad things to do, not really production-ready code. So the first thing, what I'm going to talk about is data store tips. And I'm going to structure this first, things that we've actually seen, things not to do, and then some general tips of things to do. Now, the first thing I get asked are, what are some general strategies when I'm actually writing my models for the data store? And what I always try to tell people is, think about the pages that you're serving to the users, and try to design your models so that those pages are served efficiently. And of course, pages that you rarely see, you shouldn't spend as much time optimizing as pages that you see a lot, because those are going to be the bulk of your requests and the bulk of your costs. And this isn't really related to optimizing your app per se, but everyone wanted me to plug. Make sure you put your app on the higher replication data store, or migrate your app, because now you can't really create apps on the master-slave data store. But this is going to be the most important of all, because you want your app to be reliable above everything else, and the HRD data store will help you do that. So I have some specific examples of things I'm going to go over, and I'll just dive right into those. This is my first data store anti-pattern. And it just generally generally looks something like this. You have a query, and you're fetching one result. And basically what this code's supposed to say is, I know what model I want to retrieve to the data store. So I have to ask myself, why am I going to query for it? Instead, we have something called a data store get. And here I have a get by key name, which is something I can set when I create the model. There's also data store IDs if you don't set a key name. If you know what the model you're expecting is, you really want to try to write your app so you can use as many gets as possible. And the next slide really shows the reason. If you look at what happened when I did a query, well, I did 2 data store read ops, and it took me 59 milliseconds because I had to scan through some indexes. After 1 data store fetch op and 4 milliseconds. This is really a no-brainer. 50% less and 14 times faster. So this is what I mean. Cost and efficiency, not always contradictory. Of course, for Python, really this is something that's language specific. Don't use fetch at all. Fetch actually calls another function called run and then puts it in a list. So you can just call run directly, which returns a generator, and that's going to be less memory for your application, and anecdotally, no guarantees, it's about 10 to 15% faster because it uses an asynchronous prefetch, which is something that Greg's going to cover a little bit later, asynchronicity. But this is something to call out specifically for Python. Now, my next data store anti-design pattern is something that you may not be using in your app today because it's something we just, I think it was 2 or 3 releases ago, something called projection queries. Projection queries are really good if you're reading data only and it's a small entity. This first thing is what an old query would look like on App Engine, a model where, and then the filter thing. Now the second one looks very familiar to those of us who love SQL, which is I'm actually just selecting the fields I actually want to read. This again was something not supported until recently, but now that it is, if you just if you just want the newest update of Firefox, I think we can wait. Let's go back to full screen. OK. So I just want to print out these 2 fields from my model, so that's all I'm going to retrieve, text and author. And the big news here is the first one is a full data store read op, which is 7 cents for every 100,000 ops in App Engine pricing. The second query, 1 cent per 100,000 ops, 85% less. And this is something that's really easy to switch out. But again, one thing to know about projection queries is you can't write to an entity return from a projection queries. So something to be aware of, you can always, if you find something you want to write, fetch that entity and write it. Or you don't have to replace it everywhere, but where you can use it, you really should. OK, one of my favorite / least favorite anti-design patterns. Something that looks really natural to all of us, limit offset. And it seems like a good idea, except what happens in App Engine when you specify an offset is it scans through those first 10 indexes and then reads the next 10. So basically, you're almost doing 20 results worth of work with this query. What we haven't said in App Engine is a data store cursor. What cursors do is they return the place where that query left off to you. So the next time you go to run that query, you can specify that cursor so it knows where to start from. And again, this is something where you see here 20 fetch ops in the first example because we're doing almost all of the work of the query. And after, we're just doing the 10 that we want. And it's 47% less, 13 times faster. So now we're going to get into some things that you can really do that will help improve the efficiency. And you remember one thing that I talked about was minimizing the amount of work you're doing when serving a page. So we've recently introduced something that's called embedded entities. And it's a way to store structured data within a model. And what this really can help you do is denormalize your data in a sensible way. So in this case, what you see is a contact where I want to store addresses within a contact. So I may want to store these addresses elsewhere or use them somewhere else, but I can also store this model in my contact, and if I need to put all that on one page, all the information is there, one query, it's really great. Now this isn't something that's going to save you any money, but it is something that's going to help your app run faster. And the last thing I want to point out is don't index things that don't need to be indexed. When App Engine serves results, it always serves them from a pre-computed index for a query. So usually what we do for most models on a property is we write all of the indexes every time you create or update that. But you know there are some things that you're not actually ever going to want to query on. In this case, I have something called a display name. That's just something that probably is supposed to look nice on the page that I want to store in my model. I'm never really going to query on this, so why am I going to write an index row every time I update this model? So by simply putting index equals false here, when I update this, that index row won't get written. Now, I won't be able to query on it, but in this case, I don't care, and I've also saved myself some money because I'm not writing an index. Of course, now that we've covered some data store stuff, we can do better, because the data store is still a lot of work, and so you can actually add a layer of caching on top of the data store. It's caching, 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 because there's actually 3 different kinds of caching we're going to cover. The first one is something we always are talking a lot about. It's memcache. Memcache is a fast memory cache that we have available. It's basically something where you can place something that that is hard to compute, but you're frequently reading, either from the data store or URL fetch or anything, but we use the data store here. So in this case, I took like the guestbook example, and where you're reading greetings, and we're serving the greetings every time you hit the guestbook. So there's no need to pull all those greetings from the data store every time, even if it hasn't been updated. So what I can do instead is simply add all of that data to memcache and pull it when I look for that page. And if it's not there, I can always read from the data store. Memcache doesn't take that long of a time. I do want to point out one thing that I've done in this example, which is instead of actually storing the models in memcache, I've stored some rendered HTML. And the reason I do this is a gotcha that we see sometimes, which is memcache pickles your data or serializes your data. So what happens is if your model has changed between writing and reading from memcache, you might get in trouble. This is one way to get around it, or it's just something you can be aware about when you update models on your live serving application. The next thing I'm going to cover is instant caching. Well, what's instance caching? This is basically the memory of your App Engine instance, and it's storing something in that memory when the instance is alive. It allows you to have your own eviction policy. Something I didn't mention was memcache was a least recently used evicted. In this case, storing something as a global variable, it allows you to store it the way you want it. It is also faster than memcache. It's, well, near instantaneous. I mean, memcache is pretty fast, but there may be some times when you want it to be faster. In this case, you can just store it as a global variable in your instance. But for those Python users, really what you need to be doing is using NDB instead. I've used usually DB examples in most of my code samples because NDB is relatively used. But I've actually written here what a real memcache storing and reading algorithm would look like. I'm not even going to bother to go through it because it's got like locks and tombstones and all this crazy stuff. But it's actually hard to get this right. Storing things in memcache, storing things in instance caches, things being written, having to update. NDB actually is doing all of this for you. So if you're a Python user and you're not using NDB, check it out. Hopefully it's pretty easy to translate one to the other, and you'll get a lot of really cool savings. I don't know that much about Java, but I hear Objectify has some of the same stuff, so you should check that out too. And finally, here's just a summary of what the differences between data store, memcache, and instance caching are. You can see here the latency. Obviously, data store has the biggest latency, but also you're storing the most things there, and you know, it's written there and it's written near forever unless you choose to remove it. In terms of the storage, something to call out in instance caching specifically is we do allow you to have larger size instances in App Engine. The smallest size is the default, but we do have bigger sizes that cost more money, that have more memory available. And one thing you could do with that memory is store some stuff in there to make your application faster. And the last thing I'm going to cover in caching is something that really will have a huge benefit for pages of your application that are rarely updated with new content, which is set cache control headers. It's such an easy thing to do, but what it does is when that request is sent to intermediate servers and browsers, it tells those servers and browsers how long to hold that page before re-requesting it from the server. So that means that your app's actually not going to have to really do almost any work for these requests. You get those requests only for bandwidth in App Engine. And the thing you want to be careful, of course, is that you can't ever force these pages to be re-requested before the expiration time. So please set it reasonably. I mean, we've actually seen apps that have set it for 365 days, and of course, they set it and they realize they've made a mistake. Well, once we've served the request, it's out of our hands. We can't force the servers. We can't force the browser to re-request anyway. So make this a sane value, but still use it. And in fact, if you go in the admin console, you can go to the drop-down and do requests by type per second. And what you'll see here is it actually breaks down for this application how many static requests, but also how many requests are served from edge caching. And you can see here that those requests I'm only really paying bandwidth for. My server's not doing any work, or my instance isn't doing any work. So it's a great way to save yourself some money and save your computing power to do something more interesting. Now I'm going to hand it off to Greg, who's going to talk about batch API requests.
So what are batch API requests? Batch API requests allow you to make operations on multiple pieces of data in a single RPC. And doing this allows the App Engine servers to actually fan out your request to multiple servers. And it allows you to amortize the cost of that RPC over multiple pieces of data. So what do I mean by that? Well, I'm going to use the example of task queue here. So say, for example, I'd like to insert 50 tasks into task queue. Just simple code, goes through loops and adds them. Up the top here is a graph from AppStats. It was introduced by Guido van Rossum in a Google I/O talk in 2010, so I suggest you have a look at that for more information. But in this graph here, you can actually see each of the RPCs that's made by the application. I've actually trimmed off just after about the first 10, because that goes down to 50. As you can see, each request here is taking about 10 to 15 milliseconds. So overall, it's over 600 milliseconds to enter these actual requests into task queue. So if I change this code slightly, so I still construct all the tasks, add them to a list, but I'm using the batch API interface, which is q.add, you can see that all the tasks are inserted, but it's only taking 22 milliseconds. So it makes the requests much, much faster. So we have many APIs that actually support this. Memcache, data store, task queue, full text search, they actually all support being able to operate on multiple entities for data store, add multiple documents to an index for full text search, and Memcache you can either get or put multiple entries there. So some things you will have to be careful of when you're using the batch API with task queue, for example, is that you can actually only insert up to 32 megabytes worth of requests there. So using the batch APIs can be slightly more complicated and has some gotchas around the size and the number of things that you can add to them. But overall, it's a considerable win to both latency and it makes your application faster. So I'll just leave batch API requests for a second. I'll go on to using asynchronous workflows. So asynchronous workflows allow you to start an RPC and then continue doing work in your application. This allows you to do multiple slow operations in parallel, such as performing multiple URL fetches, as I've got here. It also allows you to perform CPU-intensive operations while waiting for the I/O to complete. This was alluded to by Marzia earlier on with data store. When you're doing a query in data store, using the .run interface in Python and also in Java, what actually happens is we do an asynchronous call to the next, to fetch the next set of entities, so that we're performing the I/O to find the next entries while you're still iterating over the previous batch that we returned. So I'm just going to go over over an example of how to use asynchronous RPCs to speed up URL fetch in this example. I'm going to give two examples of this. This is using the slightly older method using callbacks, and then I'll go over the new one. So the main thing that you need to write here for using any of the asynchronous APIs is you'll actually need an event loop that keeps track of the RPCs and calls the waitAny function, which will automatically call the callbacks when they're ready. I have the doFetch call down here, which inside it I have a closure to construct the actual callback, and I'm passing it to makeFetch call, which is the actual asynchronous version of fetch in the URL fetch API. In other APIs, the asynchronous versions are generally named the same as the normal version, so data store is get, the asynchronous version is get_async, and this follows on. URL fetch was our first asynchronous API and is thus different. So with this example here, I'm passing the callback into the create RPC function, and so when the actual call has been made and the request is finished, this callback will occur and will be given the data. So as you can see, this version here actually doesn't pass anything back from that callback back into the main function. That's actually quite difficult to do using the callback model of programming here. So I will give you, this is the new version using NDB tasklets. The main difference here is that instead of having to write your own event loop, NDB has one written for you. And in fact, it actually makes use of the new yield statement as coroutines. So all you have to do is wrap the function with this ndb.tasklet decorator, and then you just yield any RPCs. And this allows you to write programs that look like they flow straight down, but actually will be calling into and out of the event loop. So you can see this example here does the same thing. It calls make fetch call, it just passes the result back, and we've actually got the return statement here. So in NDB, with tasklets, you have to actually raise the return exception, and that results get passed back into the list down the bottom. So if we have a look at the actual before and after. So before, with fetching 4 RPCs, 4 websites, it actually takes nearly 4 seconds. Doing it with an asynchronous model, you can still do the processing in between and each of these requests. And in this case, it takes just over 3 seconds. So a fairly large saving. But if this was in your main handler, as Marzia alluded to earlier, this still is probably way too slow for you. So what you can actually, some of the APIs that support asynchronous are blob store, memcache, URL fetch, and data store. So what you may actually want to do with requests, so if you wanted to gather data from an external site and then be able to serve it as a part of your homepage request, what you may want to do is actually cache that data and actually cache it in data store. So data store, as we said before, is about 50 milliseconds per request. Whereas if you're looking at the same thing for doing a URL fetch to a slow external resource, that can actually take over 2 seconds. So the example, so what you may actually want to use offline processes for is you can actually defer updating those pages, because otherwise, when the cache expires with just using a naive solution, you would actually still have to make one person wait for that 2-second request to be able to gather it again and fill your cache. Other things you can use offline processes for are doing slow external, say, billing processes. You can also use it to make workflow systems or perform fan-in, which is described in Brett Slatkin's talk from 2010. So I will actually go over an example of how to use TaskView and actually do that URL fetching example I gave before. So I'm using NDB here. The reason I'm using NDB is that it gives the transparent caching to memcache and the instance cache. So if this was a fairly highly used property and serving on your homepage, then this actually may not have to even go to data store at all. It could already be fetched in memcache, or it could also just be in the instance cache already. So going to the getURL method, so I'll skip truncate time. It's just a helper method used to ensure that we don't create too many tasks to actually fetch this. So if we look at the getURL method, we construct a key name based on the URL. We're using SHA-1 so that way we can actually ensure that the namespace of all these keys is fairly evenly distributed. So the first step we do is we just try and fetch it from data store. So if it's there, if it's not there, we'll just go away. We'll just fetch it straight from the external resource, save it, and just return it straight away. So in the case of the first user viewing this page, they may actually have to pay the 2-second request delay here. You actually may be able to, if you were implementing this in your own code, you can actually send a 302 back to the user so that, or send a placeholder so that the page will render, and then it can actually go back to and try and re-request the page so that the user actually sees something before. So here we have if we do find it in memcache or in data store, we check if the data has expired. If it has, we just defer a task into task queue, and that will then asynchronously go and fetch the new version while we return the current version that's in the cache back to the user. And as you can see, with the update cache method, it's just a fairly simple fetch from the external resource and then blindly put it to data store. So I will now pass along to Troy, who will talk about performance settings.
Great, thanks, Greg. Everybody hear me?
No.
Test. All right, let's go to the mic.
Let's bring up another.
Test, test. All right, there we go. Let's just do it. We'll do it live. All right. Hi, everybody. I'm a senior software engineer on App Engine, and today I'm going to be talking to you about performance settings that you can set for your app to optimize for either low cost or low latency. So, performance settings are something we introduced last year. We haven't talked to them publicly, as far as I know, like in a conference setting. So there's a few of them. They're on the application settings portion of the admin console. And you can see here that there's the front-end instance class that Marzia touched on earlier. There's idle instances, and there's pending latency. So the first thing I'd like to talk to is optimizing for low latency. So why do you want to optimize for low latency? Well, it's pretty straightforward, right? You have a web UI or a mobile front end, and you want to have a very, very snappy, good web experience for your users. So the first setting that you can use is what we call minimum idle instances. And what this tells the App Engine scheduler is that you would prefer that it keep around at least this number of idle instances at all times for your application. And what these idle instances are used for is to send traffic to them when all of your active or dynamic instances are currently busy serving other requests. And so this is extremely useful for things like bursty or unpredictable traffic, such that you don't have to suffer the dreaded loading request for a user-facing request. And so what we will typically tell both internal and external partners to do is to, if they're going to have some sort of event like a Google I/O event or some sort of press or some new feature that they think is going to just drive a bunch of traffic to their site, that they temporarily increase this number in order to sort of buffer that bursty traffic, and then later on they can turn it back down again in order to save some more money. The second setting that you can set to optimize for low latency is the max pending latency setting. And what this setting tells the scheduler is that you would prefer that no request to your application wait for longer than this amount of time before being processed by one of your instances. And so again, this is something to tell the scheduler that if you really want a snappy user experience, that it not wait for an instance to turn up, but it just automatically, the scheduler should automatically provision a number of instances in order to keep the average pending latency below this threshold. And so here's an example of the instances console, which is also in the admin console. And you can see here that in this case we've set 3 for the min idle instances setting, and that is represented on the right by the availability as resident, and then the dynamic ones below that are sort of the active dynamic clones. So you can see, as I mentioned earlier, that the majority of the requests to this application have been handled by the dynamic instances, and only a few have been handled by the resident ones. Here's an example of the settings when actually setting the min idle instances and the max pending latency. In this case, the admin console is warning me because I did not appropriately set the warm-up request setting in my app.yaml or appengine-web.xml. And this is a requirement for min idle instances to be used appropriately by the scheduler, and that's because the scheduler will spin up these idle instances in the background using what we call warm-up requests. And you can read more about that online. I'd also like to touch on, just very briefly, a new feature that just came out with 1.7.0, and that is the page speed service integration. And I won't go into great depth here, but it is part of the performance settings, and what it'll do is basically will cache and do content rewriting for a number of your static resources in order to basically speed up your static content. So next I'd like to talk to optimizing for low cost. And what I mean here, everybody wants to optimize for low cost, right? But in the performance settings instance, what we're really talking about here are users who are hobbyists or people who have applications that they're not really monetizing their traffic. They're running this thing for free, and they want to just try and keep their costs low at the expense of having potentially higher latency user requests for their application. And the first setting that we have here is max idle instances. And the idea is that you're telling the App Engine scheduler that you would prefer that it not keep around any more than this number of idle instances to help serve your application. And this also factors into how we calculate the front-end instance hours charge for your application. Because if you told us, I only want 3 idle instances, and for whatever reason the scheduler put up 10 idle instances, well, then you shouldn't be charged for the extra 7. The second setting here is the min-pending latency. And what this says to the schedulers, you would prefer that the scheduler allow requests to wait at least this long before causing a loading request and spinning up a new instance to serve the request. And what this does is basically maximizes your utilization of the instances that you already have to try and keep costs low. So again, here's an example of me setting these. I've set the max idle instances to 3 and the min pending latency to 750 milliseconds. And at this point, I'd like to just take a brief moment to say that while I have specific numbers here of 3 and 750 milliseconds, these are not generally applicable to all applications. They are just examples that I've chosen. The right number for your application is completely dependent upon your application. And we encourage you to try and experiment with these settings in order to find the appropriate value for your application. Next, I'd like to talk about a very serious anti-pattern that we've seen far too many times in the wild. And this is basically using both the low cost and low latency settings together simultaneously for your application. And the problem with this, and you can see what I've done here, is that both min and max idle instances is 15, and the delta between the min pending and max pending latency is 50 milliseconds. And the problem with these settings is that it confuses the App Engine scheduler so much. It just doesn't know how to operate within such a thin margin of these thresholds. And what you see as the App Engine admin is that your application, the scheduler will spin up these instances for your application, but they'll be extremely short-lived. They'll come into existence and go out very, very quickly while it tries to basically satisfy these 2 thresholds. And it basically makes a bunch of churn in the system, and it also will devalue things like instance caching because your instance cache won't be around that long. So our recommendation is to not do this. Our recommendation is to do something like this where you use just the low cost or just the low latency settings and you set the other ones to automatic. So now I'd like to talk about App Engine servers, which is an ongoing project right now, and how it will affect the performance settings that you can set for your application to make them more powerful and more flexible going forward. But first, I'd like to talk about the motivation for why we're doing this. And the only way to do that is by talking about what today's App Engine hierarchy looks like. So as you can see here, we have a top-level application. Each application has some set of backends and some set of versions, and each of those has some set of instances associated with them. And as a lot of you know, if you've been playing with the performance settings before, only the default version receives the performance settings that I talked about just now. And so what we've heard from customers from talking to them and getting feedback on the architecture as it is today is that one of the things they really don't like is that they only have a single version that will auto-scale for them, and only a single version will receive the performance settings. So all of the non-default versions, they don't get these performance settings. So what we've done is we're going to move to a world that looks more like this, basically. We're going to introduce a new level, which is called a server. And what a server is it is a conceptual grouping of versions. The idea being, though, that in this new world, the default version of a server will now be able to receive the performance settings and have those be active, and also be able to do auto-scaling. So you can have multiple servers with multiple default versions, or a single default version per server, but each of those will be able to scale independently of one another. So for example, you can have a server with a default version that is for your batch work, for your MapReduce, and those performance settings can try to utilize the instances as much as possible, because all you're trying to do is get throughput, right? You don't need low latency, you just need throughput. Similarly, you continue to have your web UI front end that has extremely low latency and high min idle instances in order to handle bursty traffic and give a really snappy user experience. And so to give an example of what these might look like in the future, like how we're going to do performance settings in the future, is that we're going to actually take them from the admin console and put them into your app.yaml or your App Engine web XML. And so when you upload your code, you will also upload the performance settings that you feel appropriate for that code. And to give an example of that, here is, for example, my mobile front-end server. So you can see here this is in app.yaml, but there will be the equivalent in the App Engine web XML. And you can see here, though, that there's a new field called server, and this is my mobile front end. We're going to have also a new section called server settings. And so you can see here it's exactly the same settings that we had in the admin console. In this case, I've set to an F2 and 25 min-idle instances and the max pending latency of 250. The automatics are there just for completeness, but are actually unnecessary. Those are the default values. And so this is an example of what today is traditionally called a backend. This is what it will look like in the future. We're actually going to move the settings from what is today in backends.yaml or backends.xml, and we're going to put them into the actual app.yaml or App Engine Web XML going forward. And so in this case, you can see this is my Geo backend server. It has 10 instances, static, just 10 instances, no auto scaling. And it has an instance class of B8 because I need a bunch of memory to do a bunch of great geocaching. And so just to recap, Marzia covered a lot of great data store modeling patterns and anti-patterns, and along with a number of caching techniques. Greg talked about the batch APIs, some of the asynchronous APIs that we have, and some offline processing techniques. And I covered today's performance settings and what they're going to look like in the future. And so with that, we'd like to thank all of you for coming. It's been a pleasure to talk to you today. And we would like to open up the floor for questions. I'd like to say very briefly, though, if you have a question that pertains specifically to your app that you don't think would apply to other people in the room, that you come find us afterwards, given this is kind of a forum and we want to answer general questions as much as possible. So thank you very much.
You were talking about just selecting certain fields and that it's much cheaper. I'm wondering why...
Hello? It's on? Oh, projection queries?
Yes. Could it be also cheaper than a get, or is it just for querying?
They're both small data store ops, so they're basically equivalent. But obviously, if you are going to, you should always use gets first, but if you have to do a query, then using a projection query is going to save you money. If your entity is sufficiently small, it's the best, because sometimes projection queries can take slightly longer if the entity is too large.
Right.
But for only a few fields, it's a small op versus a read op.
And if you do a query and you do it on keys only, and then do the gets separately and interleave with memcache, would your recommendation be just to do a projection query or do a key-only query and then try to find the entities in the memcache?
So in that case, if you're doing a keys-only query and then a get, it's 2 small ops versus the 1 small op for the projection query. So I believe you'd still be better off in that case to do projection queries. Oh, and also we have chocolate, like the last session, for people who ask questions. So if you want afterwards, you can come up and get some.
Just curious if you have some debugging tips for slow queries. I often find, especially if I'm fetching a lot of information, it seems to be going really slow, and it's kind of hard to debug because it's somewhat asynchronous, so you don't really see the cost until later when you're using the information. And there's not a lot of visibility into, under the hood. It seems like when you're making queries that are, within a bunch of keys, there's lots of situations where it's ultimately making multiple individual fetches and not doing the sort of batch fetch you might expect a real SQL database to do. So just in general, what do how do I go and look and see why is this slow? Is it really hitting an index? What is it that's taking so long? Is it the amount of data that's being transferred, et cetera? Because it feels a little opaque to me sometimes.
I think queries always hit indexes, but right. But I think what in this case is when so I'm not a super data store expert, but like zigzag queries where you're joining multiple things and I'm probably not the right person to answer this in detail. Maybe Greg.
I'll just say if you want to come and chat with us afterwards, we'd probably be able to help you with that.
Okay. But I just wonder, is there something? Are there basic pages on the stats or something that show you kind of here are the queries you're making, and here's how here are the slow queries, or here's how long they're taking in general, or here's how much data you're transferring, or how many different RPCs you're actually making on the back end?
Well,
the app stat stuff that we were showing, those were like most of the clips in here with the sort of the timelines and stuff like that, which most of them were in Greg's talk. That's an extremely valuable debugging tool that you can do on a single request basis, and it does have, like, for at least for Python, it has like a full stack dump where it'll drop you to like the exact line of code that executed it. So you really can't drill down and say like, oh, this query took a really long time, it executed out of order with this other one, and so this is the one I need to really find, and it will tell you what line of code that is. Cool.
But I also think it's worth, I mean, so there used to be more queries that required composite indexes that then they made not required. But you can still re-add composite indexes for some queries. Those will write more indexes, but they might be faster. But again, it's like there's a lot of dependencies there that I'm probably not the best expert to tell you, but that is one option also. When it used to require a composite index and now no longer does, adding back the composite index might speed up the query in that case.
Got it. Thanks.
Yeah, I had a question. I'm wondering if you had any plans of reducing the pricing maybe, or maybe offering tiered pricing for like things like games where it's harder to monetize at the rate that the current pricing is?
I mean, we have no plans on reducing pricing right now as far as I know. We're always evaluating. We know that, we just came out with new pricing for compute engine and stuff like that is tiered. So that seems to be the way that things are going, but we have nothing to announce today, unfortunately.
Great. Thanks. I've noticed whenever I configure a resident instance with the min idle instance, my app at like 2 in the morning when no one's hitting it and I have an idle instance that I'm paying for, if I hit up my app, it prefers to just spin up a dynamic instance instead of kind of using what I'm paying for.
So the min idle instances are really more geared toward handling bursty traffic. So we always prefer dynamic instances, but we keep the idle instances around in case we haven't predicted correctly whether or not there's enough dynamic instances around to serve it. So that's really the purpose. What I always kind of use in as examples, like if you're launching a website and you might have a really steep, really sharp jump, and it's hard for us to predict exactly how that's going to go. So then you might want to spin up a lot of idle instances because those instances can serve a request kind of in a pinch. But when you have traffic that's more steady state or easy kind of flowing traffic, the idle instances aren't as useful because we're usually really good at predicting when to do a dynamic instance.
So it's for burst, not startup time.
I mean, it's for both, but you should think of it as something that can serve a request while the dynamic request is spinning up.
Bingo. Okay, cool. Thank you.
Front or back?
Oh, hello. Thank you for App Engine. And you said not to use limit and offset, obviously, because it's very inefficient, right?
It's just really offset in that case.
Oh, offset. That's right.
Yeah.
Yeah,
Limit's fine.
Yeah,
Just
that's right.
offset.
I meant that, yeah. But what about if you want to page back and page forward? Cursor, you use cursor, right?
There's a start and end cursor, both. I just use the start cursor.
Right, start cursor, but let's say you have a pay and you want to go backward in can you go backwards and forward? The cursor only goes forward, right?
No, you can set an end cursor on a query. That's what she's saying. So by default, it's like there's start underscore cursor and end underscore cursor. So you can say that I believe it's that at the end, like basically of your query, you should have that cursor should be the end of it, I believe. I know I'm not explaining that very well.
Yeah, but you can't always do that. Yeah, I'll ask afterwards. Thank you.
Oh, okay.
Is server configuration enabled now or next version?
So the server configuration is just what we're working on implementing now, and one of the main reasons to bring it up is because, I think we really are looking for feedback on how that might be the most useful for you and give you an idea of what we're thinking about in the future. We don't have a target release date per se.
Yeah, we're working on this actively right now. If you'd like to talk more about it, I encourage you to come find me after we're done here, and I'd love to hear feedback that you have on it or thoughts. Definitely. That goes for everybody.
Is there any way to visualize pending latency? The one that you don't see in the request and to me it seems is nowhere reported. Also on the dashboard, right? It's
in the logs. And what I would actually plug for here is actually, we don't have this, we actually haven't written this, but it's probably really useful, is we have a logs reader API, which actually allows you to either like map reduce or read through your logs. And you could do something like read the pending latency field, like read all your requests, the information about your requests, dump it into something like BigQuery, or even write a custom kind of visualization for those kinds of logs. I mean, the raw tools for this stuff is here, but it's kind of very nascent in terms of making these like really easy to use for you, but it's possible, and I think it's like really exciting to be able to read your logs, dump them into BigQuery, do queries, and I think it's something we want to enable better in the future. But obviously, you guys could do it now, and there's always open sourcing it. I mean, not to plug it, but this is something I really want to use and haven't had time to write. So if you wanted to write it, you could, and it would be really useful both for your own application and for other people's applications.
Yeah, well, it's not well visualized in graphs or anything like that, like on the dashboard. It is, like she said, it is not only in the logs API, the data you get back from there, but it is in like the logs reader in the admin console. It's right in the first line of every request, tells you like a pending it's like pending underscore MS.
If it's sat in the pending queue, it's
Yep.
pending underscore latency in the logs.
I'm curious about the implementation of embedded entities and how the performance characteristics would compare to other kind of straightforward options that you have right now, like JSONifying an entity or pickling it and shoving.
So the embedded entities are actually just another data store model that's just been serialized and then stored in a blob field. Well, sorry. For local structured property, they're stored in a blob field in the object, and you can actually compress that if you want. For structured property, we take the name of the properties and we sort of mutate them so that we can actually still allow you to do queries over that. So as for the performance, the serialization time is the same as it would take to serialize the two entities. The write performance for local structured property is just the amount of time required to put that data. With local structured properties, because there's no extra indexes, you don't have to pay the time waiting for those indexes to be written to propagate. But other than that, yeah.
So you talked about local entities, local structured entities, which you said is a denormalized data. So what happens when you write it back? Does it again redistribute it and write it, or do you write it in one place? Let's say, for example, you have blog post and you have a profile information. Profile information being a local entity into
So it only writes it in the place you write it. I didn't really cover how you might use this like in a fully to denormalize. It's just to point out how you can store a structure. When you put it in the one entity, it just writes that one entity. It doesn't update it everywhere. You still have to do that yourself. But it's really nice because it gives you a nice logical way of understanding and structuring this to facilitate denormalization, which obviously helps with queries. So I didn't cover that.
The max limit of writing 100 or 1,000 entities per transaction still applies when you write it in
so with local structured property, it actually only counts as a single entity that you're writing, but you still have to adhere to the 1 megabyte per entity limit. So you can actually have as many values in that local structured property as you want, as long as they will fit within the 1 megabyte size limit of the entity that contains that local structured property.
So if I have 1,000 blog posts and if I write one profile which is 1 MB, it's still fine. So you don't have to worry about writing it as 1,000 megabytes, right? Am I making sense here? Or?
I'm not sure that we understand exactly.
Okay.
So the structured property is stored within the one entity.
Think of it like a blog post and a profile information.
Right.
A profile information lives inside the blog post because you want to denormalize it just in case you want to query.
Right.
So if you have to write a change to the profile information.
You'd have to write it everywhere.
Oh, okay, 1,000.
That's not a reference.
Yeah.
So I have a question about queries. Let's suppose I have an entity with 10 fields. I'm assuming if I query all 10 fields, it's a full entity read, right? What determines the threshold? If it's a small read or...
If you use a projection query and you actually call out all 10 fields, it's still just the small op. The thing that might happen there is the index scans might take a little bit longer, so it might not be faster, but it will be cheaper.
Awesome, thank you.
Wait, 7? It's... No, it's one small op. It's one small op. We had Alfred.
There was an issue where, I forget what version, but the static files in the log were no longer showing the refer in the access log. Is page speed going to fix that, or is that going to still have that issue? Or?
Do you want to answer it?
Page speed, I think, is orthogonal.
Sorry.
But
for that specific issue, I know the thing there was that we do not get every piece of information that we have for normal requests for edge cache requests. So if you have billing enabled, you're serving a static resource, and it's coming out of our edge cache, we don't necessarily have the response size or the referrer, or I think the user agent field. So some of those are missing.
yeah, so page speed is actually our integration with the other Google service page speed. So that is totally kind of unrelated to this issue. What that does is that uses that service to compress like CSS files and sometimes JavaScript files and serve them from the page speed cache. So it's really quick. So these two issues are not related.
Just a small comment on my question before with graphing pending latency. I just checked. Actually, the latest Prodigal library allows you to graph out the pending latency, just as FYI for everybody who was wondering.
Cool.
Yeah, thank you.
Great, thanks. If you're already minifying and combining your JS and CSS files, does page speed give you any advantage?
I'd refer to the documentation on this one. I know that basically they have a number of options that you can choose depending on like what you want to do. For example, there's like CSS inlining, and I don't know if they do spriting or anything like that. But I mean, basically each individual option does some optimization that is separate from the others. So it really depends on what you're looking for.
Would it be an advantage putting it in the page speed cache?
Yeah, I mean, caching is always good, right? So yeah, I mean, it would be an advantage to put it in the page speed cache. Yeah.
Okay, I'll experiment with that. Thank you.
Yeah.
Okay. I think there'll be better documentation forthcoming, but the page speed service is very, very similar to the open source page speed mod page speed Apache plugin. So the sorts of things there are exactly what we're exposing, just built into your app.
I'm already using the Google Closure tools that does a pretty good job already. But, that would be a nice.
All right, thank you very much. If anyone else wants to...
Yeah, if you asked a question, remember to come
we'll
get your chocolate bars, and if you want to come talk to us individually, we'll be here. Thank you.